So dear student, I Rakesh Jain from Gyanware University. Today I am going to teach you about the derivation of Wein bridge oscillator. What is the meaning of oscillators? How many kinds of oscillators? What is Wein bridge oscillator and how to derive the basic formula for frequency of oscillation in case of Wein bridge oscillator. So first of all, oscillator is a device in which generate the waveforms which provide the output without any input. So it is a special kind of device because without the input it can generate the output. It basically changes its output or generate the output on the basis of the feedback used. Actually oscillators uses feedback, positive feedback. Basically the meaning of feedback is when some part of the output again applied at the input so as to change the output again, that is known as feedback. Basically there are two kind of feedback, one is negative feedback and second one is the positive feedback. Negative feedback generally employs in the amplifier circuitry and positive feedback are employed in the oscillators. Because today our topic is oscillator though, so that the basic meaning of oscillator is without input, a device which can provide the output. Oscillator uses which kind of feedback? Definitely it uses positive feedback. Basically, oscillators are of two types. One is sinusoidal oscillator and the second one is non-sinusoidal oscillators. The oscillators which provide at the output a sine waveform, a sinusoidal shaped waveform, that is known as sinusoidal oscillators. And those oscillators which provide some trigger pulse instead of a sinusoidal, they can provide another kind of pulses, that is known as non-sinusoidal oscillators. Basically the types of sinusoidal oscillators like Wein bridge oscillator, RC phase shift oscillator, Hartley oscillator, Colpitt's oscillator, tuned collector oscillator, beat frequency oscillators, these are some sinusoidal oscillators. And the second one is non-sinusoidal oscillators like multivibrators like a stable multivibrator, monostable multivibrator, bistable multivibrators. Those multivibrators are non-sinusoidal oscillators. Blocking oscillators are also in the category of non-sinusoidal oscillators. So let us start our journey with this MS Paint file first of all. So just to see. Okay, I'm telling you that I use a mobile to communicate you properly and use a computer screen in front of me to type on MS Paint file. Okay, let's see this MS Paint file first of all. Now, are you all are able to see this MS Paint file? Oscillators is our topic. So I begin by writing down some points, some key points related to oscillators. That oscillator is a circuit which provide output, or we can say output signal or output waveform, output without input. Oscillator uses positive feedback, right? Any oscillators to sustain the oscillation must satisfy a criteria that is known as Bar-Hussein criteria. To sustain oscillation, the circuit must satisfy Bar-Hussein criteria. It is also known as Bar-Hussein criteria to sustain the oscillation. To sustain oscillation, the circuit must satisfy Bar-Hussein criteria. Now, what is the meaning of Bar-Hussein criteria? So, Bar-Hussein criteria is what? Let's suppose to understand that oscillator. Let's suppose this is a block which consists the forward amplification gain as E. Okay, this is the input to the circuit, and this is the output. If again the output applied at the input side, so let the this input is what? This is a feedback input. Okay, this beta is in the feedback network, and this A is in the forward gain. So the total loop gain must be A beta. Okay. So what is the Bark-Hussein criteria? Actually, in Bark-Hussein criteria, there are two things. The first thing is the loop gain. The total loop gain must be 0 degree or 360 degree. Okay, I just write down here. In Bark-Hussein criteria, there are two things. The first thing is the total phase shift around the loop, that is feedback loop, must be 360 degree. Okay, I just 360 degree or 0 degree. That must be 360 degree or 0 degree. The total phase shift around the feedback loop must be 0 degree or 360 degree. This is one criteria for the Bark-Hussein, and the second criteria, these two together, is known as Bark-Hussein criteria. The total loop gain must be unity, greater than or equal to unity. The total loop gain must be equal or greater than unity for proper oscillation. What is the meaning of this one? The total loop gain in the forward path, the loop gain, the forward gain is A, and in the feedback path, the gain is beta. So the total loop gain is A beta. That must be, we consider positive. So I draw the bar sign over there. So the total loop gain must be greater than or equal to unity. Okay, so these two criteria must be satisfied for an oscillator to sustain the oscillations. Okay, now we are talking about the types of oscillators, the kind of oscillator or the classification for the oscillator. So basically the oscillator can be classified as into two categories. Basically, one is the general oscillator, means those who provide the output waveform as sinusoidal. They are known as sinusoidal oscillators. So one is the sinusoidal oscillators, and the second one is non-sinusoidal oscillator. The first is the sinusoidal oscillator and the second one is non-sinusoidal oscillator. These are two categories for the oscillators. If you further classify them, the sinusoidal oscillator may be of different types. Like they may be of those sinusoidal oscillator whose construction consists resistive and capacitive devices, resistance and capacitance. They are termed as RC capacitors, like RC phase shift oscillator, RC oscillator, like RC phase shift oscillator, Wein bridge oscillator. So they are RC category kind of sinusoidal oscillators, and those which consist the reactive element like the inductance L, capacitance C, they are termed as LC oscillator. They consist of a tank circuit which is responsible for the to sustain the oscillations like Hartley oscillator, Colpitt's oscillator. But here we just write down them in directly as a name in sinusoidal oscillator. So there are different kind of sinusoidal oscillators like Wein bridge, RC phase shift, Hartley, Colpitt's, tuned collector, crystal oscillator, etc., etc. These are different kind of sinusoidal oscillator. And the non-sinusoidal oscillators can be of types like blocking oscillators, multivibrators, etc. These are different kind of non-sinusoidal oscillator. But here, first of all, we should begin our journey for oscillations with to find out the derivations for the Wein bridge oscillator. So we are talking about the sinusoidal oscillator. It means sinusoidal oscillator like Wein bridge oscillator are that oscillator which provide the sinusoidal waveforms. So sinusoidal oscillator provide sine waveform at the output. The frequency at which this sinusoidal waveform will be generated the output waveform consists of a frequency that sinusoidal sine wave consists of the frequency that is known as frequency of oscillation. Okay, so today we are talking about the Wein bridge oscillator. So I am open a new page. Okay, wait for a while, just to save this file. Okay, now see the Wein bridge oscillators. Right. So first of all, the Wein bridge oscillator is a sinusoidal oscillator. Wein bridge oscillator, it is a sinusoidal oscillator. The same term can be used for that. First, it is a sinusoidal oscillator. Right? It must satisfy the Barkhausen criteria to sustain the oscillation. Yes. Third thing is, it is a RC kind of oscillator. It consists of resistor and capacitor element, that is a kind of RC oscillator. It also provides the output without the input, and because it must satisfy the Barkhausen criteria, it means the total loop gain must be greater than or equal to unity, and the total phase shift around the loop must be 360 degree or 0 degree. 360 degree or 0 degree. Okay. Now we just see the basic diagram of Wein bridge oscillator. Yes. It provides the sinusoidal waveforms. Right? Okay, now the basic circuit diagram for the RC Wein bridge oscillator is like this one. Here we use for the amplification. Basically, any oscillator circuit consists of two things. One is the amplification section, and second one is the feedback section. The amplification section may be a transistor or any amplification device. Like here, I will teach you with the help of operational amplifier use for the amplification section. And the feedback network in case of Wein bridge is a resistance and capacitance network. So it is a bridge kind of structure. That's why there is a name Wein bridge. Okay. Now see this one, the circuit diagram. So first of all, this is a basic basic operational amplifier symbol. This is the inverting input, and this plus sign show the non-inverting input. We know that 741 operational amplifier 741 is a IC that is known as operational amplifier IC, in which the pin number 2 behave as an inverting input and pin number 3 behave as a non-inverting input. Pin number 7 behave as a plus voltage to provide the supply, positive supply, and 4 number terminal is for the negative supply. I just mentioned the pin number also. This is 7, this is 4, This is 2 number pin, that is inverting input pin, and this is 3 number pin, that is non-inverting input pin. And from the 6 number pin, we will taken the output. This is the basic symbol of an operational amplifier. Here we use an operational amplifier for the amplification section. And the feedback network must be a bridge kind of structure like the Wheatstone bridge, in which only resistance and capacitance network are there, such that one arm of the bridge consists resistive and capacitance in series, and one arm consists resistance and capacitance in parallel. So like this one, that this is the arm in which resistance and capacitance are in series. Okay, and this is another arm in which the resistance and capacitance are in parallel. The rest of the two arm consist resistive element only, in which when we will design the Wein bridge oscillator, then one arm can consist a variable resistor. Okay, so these are four arms of a bridge. So this is a feedback network for the Wein bridge oscillator. So let the name of this resistance is R1, let the capacitance is C1, this resistance is R2, and this capacitance is C2. This is R3 resistance, and this is R4 resistance. Now we have to connect the amplification section with the feedback section so as to complete this circuit, overall circuit. So this arm will be consist with the inverting input. This arm will be connected with the non-inverting input. This arm will be connected to a ground. And this arm will be responsible to provide the feedback. Means some part of the output will be applied to the input via this feedback circuitry, and this arm is connected to the pin number 6. And when we will taken the output from this circuitry, we that the voltage can be denoted as V0, then we will find a sinusoidal waveform at the output. We will find the sinusoidal waveform at the output. Sorry. Okay, right. Now we have to derive the formula for frequency of oscillation. Okay. So first of all, remember the basic balance condition for a bridge. Let's suppose from this black color, I'm just showing you the rough part. Let's suppose this is a Wheatstone bridge in which there are 4 arms, in which there are 4 resistances. Okay, this is, let's suppose, Rx arm. This is Ry. This is, let's suppose, Rp. And this is RQ. There are 4 resistors, and galvanometer and input are connected. Okay, so the bridge condition is said that whenever the bridge is in balance, then this Rx RQ must be equal to Rp Ry. That is a balance condition. It means the resistances which are parallel to each other must, that are resistances, multiplication of those resistances. Okay, what I want to say, I just write down. It means this arm, that is Rx, and parallel arm is RQ arm. So this will be R. The main this resistances. Now here in this Wein bridge, we have a Wheatstone bridge kind of arrangement. Definitely, to find out the frequency of oscillation, we must consider the balance condition for that bridge, and it must satisfy the same kind of condition, that the opposite arm resistances. But here we use reactive element also, like the capacitances. In one arm the capacitance is in series, and in one arm capacitance is in parallel. So instead of using the terminology as the opposite arm resistance multiplication must be equal to the remaining arm resistance multiplication, we must use the term impedance, because reactive element is also there. So what should be the balance condition now? The balance condition of this Wein bridge feedback network must be such that the opposite arm impedance multiplication must be equal to the remaining opposite arm impedance multiplication. Okay, so I just remove this. Okay, I just save this file and open a new file in which I will derive the derivation. In the new file, I just wait for a while. Okay, so this is the Wein bridge oscillator whose derivation we must have to perform. Now I remove this rough work. Okay, so this was our Wein bridge. Now to derive the frequency of oscillation, definitely we should use the feedback network only. So where is the feedback network? Feedback network is only this one. So I just remove the remaining part, and from with the help of the feedback network, we have to prove how the frequency of oscillation formula comes, because that all work depends on the feedback network, which is responsible to sustain the oscillation. Okay. So this is the feedback. Now, to find out the frequency of oscillation, we should balance the bridge, and the condition for balance the bridge is the opposite arm impedance. For example, this R1 C1 first arm impedance is denoted by Z1. This fourth arm impedance is denoted by Z4. This third arm impedance is denoted by Z3, and this second arm impedance is denoted by Z2. So from the frequency of oscillation, from the a balance condition of a Wheatstone bridge, we can say, what I want to say, that Z1 multiplied by Z4, the opposite arm impedance multiplication must be equal to the remaining opposite arm impedance multiplication, that is Z3 Z2, or we can say Z2 Z3. Okay, now what is the Z1, what is Z2, what is Z3, and what is Z4? See, here R1 and C1, one passive element and one reactive element, one resistance and one capacitance is in series. So what should be the impedance Z1? The impedance Z1 should be R1 plus 1 upon j omega C1. J omega C1. Okay. Now it should be multiplied by Z4. What is Z4? Z4 is the fourth arm impedance. But here only a resistive element is there. So we, in impedance, we should write down only the resistance. Z4. Okay. That must be equal to Z2. What is the second arm? I am talking about this arm. What is the second arm impedance? The second arm impedance is we have to calculate, because one resistance and one capacitance are in parallel. So what is the impedance? The impedance is R2 divided by, whenever one resistance and capacitance are in parallel, then R2 divided by 1 plus j omega CR2, that is j omega C2 is the name of the capacitance, and R2 is for resistance, so C2. And that is Z3, so the impedance is R3. Okay, so now we have to multiply. This R1 will be multiplied by R4, so as to find out R1, R4, R4, then plus this 1 upon j omega C1 will be multiplied by R4, so that it will be equal to R4 divided by, so I just write down divided by j omega C1. So that is j, let's suppose this is omega. Instead of W, you should consider as omega, because I am typing from the keyboard. Omega plus C1. Okay. Then it will be equal to, it must be equal to, R2 R3 divided by, divided by so divided by 1 plus j omega C2 R2. 1 plus j omega C2 R2 plus j can be taken as LCM. So j omega c, this must be multiplied with R1 R4. So R1 omega R1 R4 j omega plus right hand side, it will be equal to the same term. We cannot modify anything. R2 R3 divided by 1 plus j omega C2 R2. Okay. Now multiply. Now perform the cross multiply. It will be equal to when omega C1 multiplied by 2 R will be equal to j omega 2. Then this will be equal to 1 both of all this we multiply by both the terms. So R1 R4 j omega C1 j omega C1 R1 R4 j omega C1 will be by, then the remaining term will be multiplied by j omega C2. So this R4 j is denoted as 1. So it will be equal to these two the plus I just write on minus because j to j multiplication square then square imaginary term will be multiplied to each other then will generate a minus sign. So minus omega square. So I just have to write down square over there and R R C C2 R2 C2. Okay. So R1 R2 R4 C1 C2 R apply 4. So I just shift a little bit left side. Okay. Now see the this part with 4 also. So j omega C2 R2 R. Okay. So now this is the total term which we find out from the cross multiplication. 1, 2, 3, 4 terms at the right hand side and at the left hand side one term. Okay. Now we just see the real part and the imaginary part. Which are the real part and which are the imaginary part? Wherever j is there, it means iota is there. That is imaginary part. So this is the imaginary part. This is also imaginary part, and this is also imaginary part. So we just compare the real parts. We compare here we only compare here the real parts. Okay. Now which are the real parts? See from this brown color I'm showing you. At the left hand side there is no real part, only j part is there. So at the left hand side is this R4 is a real part and this omega square R1, R4, C1, C2, R2 is also a real part. The rest part are imaginary because J is there. Okay. So I just copy them and paste. So these are the real part from the right hand side. Okay. Now 0 is equal to R4 minus omega square R1, R4, C1, C2, R2. So definitely R4 is equal to when this omega square R1, R4, C1, C2, R2 will be moved towards the left hand side. So they will be equal to each other. So it will be R4 is equal to, we just move the parts from here to there. So omega R4 is equal to omega square R1, R4, C1, C2, R2. So R4 to R4 will be cancelled out. So what will remaining at the left hand side? This R4 to R4 will be cancelled out. Wait, this R4 to R4 will be cancelled out. So at the left hand side only 1 is there, and at the right hand side omega square r1 omega square r1 r4. Okay, at the right hand side we will only have omega square r1 r4 will be cancelled out, r4 r1 c1 c2 and r2. Okay, so it means what is omega square? So definitely omega square will be equal to, I just type here, omega square will be here equal to this. I am talking about this omega square. Okay, so 1 divided by, when this r1 r2 c1 c2 will be moved at the left hand side, it will be r1 r2 c1 c2 r1 r2 c1 and c2. Okay, we know that. And what is omega? So whenever it will move shift a little bit, then it will be, when this square will be taken, when the square root of both the right hand side and left hand side will be taken, then from the left hand side this square will be the right hand. Okay. Now the last step, we know that omega is equal to 2 pi f. We always remember that omega, the frequency in radian, should be equal to 2 pi f, where f denote the frequency in hertz or kilohertz. F, so pi, so, so 2 pi f will be equal to 1 upon r1 r2 c1 c2. So this 2 pi f will be equal to this. So what is f? Definitely f is equal to 1 divided by 2 pi will be removed at the right hand side, under root of r1 r2 c1 c2 r1 r2 c1 c2 r1 r2 c1 c2. Okay. Okay, I just decrease some font size so they can be shown there. Okay, so 2 pi 1 upon 2 pi root of r1 r2 c1 c2. This is the frequency of oscillation formula for a Wein bridge. One more thing you should remember that, yes, this is the frequency of oscillation formula for the Wein bridge. Now, if we consider that this R1, R2, C1, C2 are equal to each other, for example, here instead of this R1, we use R resistance, and C1 we use C. This R C2 and C1 are equal to each other, that is equal to C, and R1 and R2 are equal to each other, that is equal to R. Then what will happen? Then the formula will be modified, that this r1 r2 will be from this red color, see, this r1 r2 will be multiplied as r square because both are equal to r. So under root of r square will be r, and similar to this c1 c2 will be multiplied as a c square because c1 c2 equal to c2 equal to c, so that the frequency of oscillation will be f is equal to 1 upon 2 pi rc. Then the frequency oscillation formula will be little bit modified, and it will be equal to 1 upon 2 pi rc whenever r1 equal to r2 equal to r and c1 c2 equal to c. So that is the derivation of frequency of oscillation formula for a Wein bridge oscillator. So I hope you understand about this Wein bridge oscillator, the basic introduction to the oscillators, and how to derive the basic of frequency of oscillation formula for the Wein bridge oscillator. So I, Rakesh Jain, wants to say you thanks for watching the video. Thank you. Thank you very much.